Okay, cool. So thank you very much. So my name is Yunzhe, and I'm going to talk about a recent work about linking replay to model-based learning. Cool. So now let's imagine if you are this rodent, and the only thing you want is this piece of cheese, okay? And things might get a bit complicated in a real-life situation. For example, you might start from all three locations, and again, the goal of your life is to get this piece of cheese. Now imagine in one situation, you start from the blue and you choose the left option and you get the chase. That's great, right? However, if you want to be more efficient, you should also know what you should do when you are being put in the yellow or the green location, right? So that's saying I should know whether the other road is also leading to the chase or not. And this does create a problem, right? Because the state and action and then the outcome are separated by both time and space. And this is a well-known problem called credit assignment in the reinforcement learning. And today I want to show you how in the human brain could we implement a model-based learning algorithm that's trying to solve this problem. And I think one potential mechanism is replay. So just a little bit background on replay. So replay is a well-documented phenomenon in rodents. So the play cells that are normally only going to fire at a given location will fire sequentially during rest, that actually recapitulating past or future experience. That's what we call replay. It's a suitable mechanism because it is internally generated. So it can quickly, and it's also time compressed, so it can very quickly bridge action and space that are, the action and outcome that are separated by time and space. All right, so how we do that? So the first thing we need to do, we need to design tasks that associate local and non-local learning. And here is what I mean. So let's say, again, I'm in the blue path and take this one. And then the path I just chosen is what I call local learning, right? You can just do that through try and error. And there are two other paths, I would call that non-local learning. It's non-local because you have the lead by passing the local outcome to the non-local actions. And the way to do it is what I termed non-local learning. And if this, and upon this problem, there is a second order question, i.e. with so many non-local experience in our life, how should we prioritize, how should we prioritize the memory access, right? Should I replay more of first to the path lead to yellow versus the green or vice versa? Luckily, this problem has already been solved by Marcello Marta and Nathaniel Dahl 2 years ago based on reinforcement learning. So they figured out a lumping model, i.e. saying the way to decide which memory should I have access to first, depending on a product of two factors. One is called need, another called gain. And need determines how often did I encounter this experience again. And the gain determines how much actual reward do I get by replay the experience. And with close collaboration with Marcello and Nathaniel, also with Tim Barons and Ray Dolan, we're trying to do that. We're trying to do that in humans. So in humans, this is the task they're doing. So we manipulate lead by gain separately. The lead is manipulated by the probability they're going to start at each of the arms. So at each trial, the participant be put in one of those arms based on those starting probability. And then the job of the participants is choose the path leading to the outcome, i.e. X and Y. And the reward probability of X and Y going to change independently, follow a random walk. So this is going to manipulate the gain. And the aim of this study, and then we can study priority. And then the aim of this study is to look at those triangles, i.e. priority, replay, and behavior. All right, so first let's talk about the model-based behavior. So we can define model-based behavior in a model agnostic way. So again, we already separate local and non-local learning. Let's say again, on the last trial, we start from the blue. And then in the current trial, if I have been putting in a different starting arm, if I am model-based, i.e. if I know the transition structure, I should more likely to choose this path versus this one, right? Because I already get a reward on this path. So this is what we can use as index of model-based behavior, while we can using some model agnostic analysis to detect that. And indeed, this is what we find. So the same means starting at the same arm as previous trial. Diff means starting from different arm. So this, the reward means get a reward last trial, unarg means didn't get a reward. So this contrast is a textbook of model free learning. So you do that through trial and error. And this would be an index of model-based learning, i.e. if I starting from a different arm, what is the probability do I going to choose the path that leading to the same outcome as the last trial? And you would imagine if I'm model-based, I would more likely to do so if I get a reward on the last trial. And this is indeed the case. And the difference between model-free and model-based in this task are indifferentiable, which means the participants indeed are really model-based in this task. Then we ask a second question. In the model-based behavior, do we see prioritization? We can further separate each of the non-local paths as high lead versus low lead, or high gain versus low gain. If we compare the learning rate of the high high priority versus the low priority, we see indeed a higher, significantly higher learning rate for the high priority path versus no priority. So this establishes the first line of this triangle, i.e. the behavior, i.e. there is prioritization in behavior. All right, so let's now turn to the neural data. So again, so this task, we want to look at the neural mechanism. So first thing first, we want to say, do we actually can decode all those pictures? And this is not a trivial task because there are 16 states in this task, right? So because there are 18 pictures in this task because there are 6 sequences. Each sequence have 3 distinct stimuli. So first we can show that we can decode all the picture pretty well with decoding accuracy peak around 50%, while the chance level is below 10%. And again, peaked around 200 milliseconds, consistent with our previous study. And the second thing we want to look at is only look at the time when the reward has been received, because this is only time in this task where new learning can happen. And if we look at those time, we can say in general, we have 2 types of sequence. So the x-axis here are the time lag. The smaller the time lag means the faster the replay is. And the y-axis means the strength of the replay. And the dotted line is the permutation threshold. Anything that past that would be significant. So you can see we can identify 2 types of replay, one in forward direction. So forward indicating as the same direction as experience, while backward means in the opposite direction as experience. And it's interesting because this forward thing will replicate our previous study doing rest that we show a dominant forward thing at 40 or 50 millisecond time lag. So it's really, really fast. But this backward one is intriguing. It's slower, it's backward. It potentially may be related to non-local learning. Now, again, in this task, we separate local and non-local learning. So the first thing we want to say is, do we see a representation content difference in those 2 replay with respect to non-local and local representation? And indeed, we say this 30 millisecond forward replay mostly encoding the local experience, i.e. the experience you just go through. So it's indeed literally replayed, while it doesn't represent the non-local experience. However, the 106 milliseconds show a distinct pattern. It only encodes non-local experience and doesn't care about the local one. And it's interesting. Then we can look at the physiological difference, right? Again, we show the 30 millisecond thing is associated with a shape width ripple power increase at 120 to 180. And this is consistent with our previous studies for the similar kind of replay. But we didn't see that for the 160 millisecond. And a few of the beamforming results, which I haven't shown here, suggest this 160 millisecond have a more cortical engagement as compared to the 30 millisecond. So this all of those indicating the 160 millisecond replay is another type of replay and is potentially suitable for non-local learning. And we're going to test that formally through a computational model. The idea is to say, does the inclusion of sequence going to significantly increase the learning, i.e. the learning rate we put on the replay, while already taking into account of the baseline that doesn't care about replay. And now we can say, do we say 160 millisecond increase non-local learning or 31 increase? So the answer is 160 millisecond sequence. The inclusion of that does facilitate learning. And that establishes another line of this triangle, i.e. replay does support and facilitate non-local learning. Okay, great. So the last question is replay actually prioritized so that it's going to most likely to replay the most policy informative behavior? Again, this can be translated in the analysis, i.e. do I replay more to the yellow path or to the green path, depending as a function of the product of lead and gain, right? And again, just to remind you, the lead is manipulated by the starting probability of the arm, and the gain is manipulated by the reward probability of each outcome. And then at each of trial, we can separate the high priority with the low priority. And when we do that and collapsing all trials, we can detect a difference in the replay that's stronger in high priority paths with low priority paths. And so we can say that, again, pick at 160 milliseconds, while this 30 millisecond thing, which is dotted line here indicated by this blue line here, is not significant at all. So this establishes the last line of this triangle, i.e. replay is indeed prioritized. It prioritized so that it first replay the most policy informative experience. All right, with that, I want to conclude. So we find non-local learning is prioritized to support model-based behavior, and we find reverse non-local replay at 160 millisecond lag help model-based learning. And it's both functional and physiologically different compared to this shape-wave repo faster 30 millisecond replay. And this 160 millisecond replay is prioritized for the most policy informative experience. And with that, thank you, and thank you all my collaborators, Kim, Nathaniel, Marciano, and Ray, and thank you.
Thank you, Yunzhe. Such a nice piece of evidence on reward and non-local replay. I'm very curious, but let's see if there is some of the questions. Yeah, there is a question by Lawrence Hunt. So I'll just read it aloud. He's saying he's trying to map your forward reverse results onto what is found during SPW and theta sequences in the rodent. Are there any example of rodent backward replay during theta that you could relate to your 160 millisecond sequence? Is that clear?
Yeah, indeed. This is a really good question. So this is a question that buffs us a lot. So the question is, so what Lawrence is trying to ask is, what is the correspondence of those human replay to the rodent one? And those 160 millisecond is intriguing because the 160 millisecond indicating a 6 hertz, right? So the speed is 6 hertz and is in the theta range. And intriguingly, in rodents, we also have those theta sequence. But normally, theta sequence is forward-looking, right? It's going right in the direction of where you are, and it's continuous while the rodent is like moving around. It's not like going to be initiated by the reward. So so what we have found is more like the shape-wave ripples in rodents because it's initiated by the reward, and it seems to have a function of backpropagating the value. But indeed, it's intriguing because we